Good day, everyone. For today's video, ang ating topic is ang ating fluid flow measurements with regards sa ating mga device coefficients and yung mga measuring devices. Okay, let's proceed.
Yeah.
So here we have our PowerPoint presentation. So we will proceed sa ating discussion. So for our learning objectives, we will understand the flow in pipes. We will define the fluid flow measurements, and we will also discuss, again, the Bernoulli's theorem and describe the venturimeter. For our introduction for this discussion, fluid flow in circular or non-circular pipes is commonly encountered in practice. Example nito yung ating So sample nito is yung water system natin, water distribution natin, even sa city or sa ating housing. So yung ating fluid flow is we will be encountered. So fluid flow is classified as external and internal, depending on whether the fluid is forced to flow over a surface or in a conduit. Internal and external flow exhibit very different characteristics. In our discussion, we will focus on the and consider internal flow where the conduit is completely filled with the fluid and the flow is driven primarily by a pressure difference. A general physical description of internal flow and the velocity boundary layer will be discussed further in our topic. So, fluid flow encompasses a wide variety of fluids and applications. Fluid flow devices fall into a number of device categories as well as fluid classes. In general, we can split the fluid into two classes. Ito yung ating gas and then liquids. The following are the known devices na makaka-measure itong ating mga variety of applications or parameters. So first is the abstraction flow meters. It is the simplest and the oldest of the measurement devices. This was modified in later times to a device known and called notch wear. Second, yung notch wear, classified by the shape of their notch. It is used to determine flows from open water sources such as streams. It is a simple measurement technique that can be used on nearly any open flowing body of water. Next is yung ating orifice. It is used to measure the pressure differential across the plate or yung sa ating or yung opening. Next is yung venturi flow meter. It is used to calculate the velocity of fluids running through a pipeline. Next is yung nozzle flow meter. It provides an intermediate pressure drop between orifice plates and the venturi tubes. Also, they are applicable to some slurry systems that would be otherwise difficult to measure. Last is yung ating pipe tube. It is a simple device that allows for the measurement of the flow pressure in a moving fluid. This device is a section of tube that measure the pressure at the tip and the pressure at the side of the tube. Okay, so next slide. Yung flow in pipes. So liquid or gas flow through pipes or ducts is commonly used in heating and cooling application and fluid distribution networks. The fluid in such application is usually forced to flow by a turbine or pump through a flow section. excuse me, we particularly we pay our excuse me again, we pay particular attention to friction, which is directly related to pressure drop and head loss during the flow through fluid flow through pipes and ducts. The pressure drop is then used to determine the pump power requirement. A typical piping systems involves pipe of different diameters connected to each other by various fittings, valves to control the flow rate, and external energy added by a pump or turbine to control the pressure of fluid flow. The term pipe, duct, and conduit are usually used in interchangeable for flow section. In general, flow section of circular cross-sectional area are referred to as pipes, especially when the fluid is liquid, and flow section of non-circular cross-section as ducts, especially when the fluid is gas. Small diameter pipes are usually referred to as tubes. These terms are necessary to be understood to avoid confusion. You probably noticed that most fluid, especially liquids, are transported in circular pipes. This is because pipes with circular cross-section can withstand large pressure difference between inside and outside without undergoing significant distortion. Para sa non-circular pipes, they are usually used in application such as heating and cooling system of buildings, where the pressure difference is relatively small. In attempting to describe the motion of fluid, one may take either two approaches. First, to follow the path of a particular particle through space, defining the location and the time of arrival. At each point, or select points in space and note the magnitude and direction of the velocity of fluid particle as they pass through pass through a selected point. By velocity, it means the change in position of water particle in moving fluid during a certain time interval. The direction of velocity vector shows which way the particle is moving at a particular time. The magnitude naman signifies how fast the particle is moving. If the succession of water particle pass through has an identical velocity vectors, we speak of a steady flow. Otherwise, it is an unsteady flow. Acceleration of fluid means a change in velocity. And there are two kinds of acceleration, since velocity can change in place as well in time. In a pipe of enlarging diameter, the velocity of the flow decreases as it passes from section of a small to larger diameter. This form of acceleration or this form of deceleration is called a spatial. Okay. May I repeat? This form of deceleration is called spatial acceleration. If the discharge flowing through a certain cross-section varies with time, we speak of a temporal acceleration. In our discussion, we will focus and assume that there is no temporal acceleration exists. This means that the flow is steady. So next, we will recap tayo sa napag-usapan na natin to sa previous video, pero balikan lang natin. Summarize lang naman ito. Summary lang yan naman ito. So work, energy, and power. Sa definition ng work, to create and maintain motion in fluid, work must be performed. There are many ways to describe work. The following are some of the common definition. So work is equals to force times distance. Meron din tayong power times time. And then work is equals to energy input minus energy output. Okay. Next, definition ng ating power. Hydraulic power generated by turbine and pump. The power is usually expressed in terms of watts. Watt is defined as 1 Newton meter per second. To move a discharge screw against a pressure of yung ating pressure na unit weight times height, the required power is unit weight times yung ating elevation head or energy head times discharge. And yung mechanical power natin is expressed in horsepower or yung ating HP. Next, yung ating energy. The ability to do work is called energy. Energy, therefore, is simply stored work. There are various forms in which energy appears in nature. Temperature indicates the amount of heat energy. Temperature and pressure are present. Temperature and pressure represents internal energy in matter. Example, a lump of coal has a chemical energy that may be transformed into heat energy by chemical reaction called burning. An object placed higher in gravitational field has more energy by virtue of its relative elevation than the same object at a lower elevation. And this is called the potential energy. A compressed spring or stretched strip of rubber has an elastic energy. The force applied to it gives the force applied to them gives rise to pressure energy. So we have here yung ating mga types of energy. We have kinetic energy, pressure energy, and potential energy, which is in terms of elevation from the datum. So next is yung ating flow through orifice or yung mga other devices. So learning objective natin dito is to understand orifice and its concepts. So an orifice is an opening made inside or bottom of the tank, having a closed perimeter through which the fluid may be discharged. It is used to measure the rate of flow of liquid. Orifice is a small opening of any cross-section, such as circular, triangular, rectangular, or etc., through which, again, the fluid is flowing. Orifices are classified on the basis of their shape, size, nature of discharge, and shape of the upstream edge. The orifices are classified as small orifice or large orifice, depending upon the size of orifice and head of liquid from the center of orifice. If the head of liquid from the center of orifice is more than 5 times the depth of orifice, the orifice is called small orifice. If the head of the liquid is less than 5 times the depth of the orifice, it is known as large orifice. So, meron tayo ditong different classification in terms of different conditions. So, the orifice are classified as kung sa kanyang shape, in terms of shape, meron tayong 4 na classification: circular, triangular, rectangular, and square orifice depending upon their cross-sectional areas. And another classification, if sharp-edged orifice ba or bell-mounted orifice, depending upon the shape of upstream edge of the orifice. Another one is free-discharging orifice or drowned or submerged orifice, depending upon the nature of discharge. And last classification, if fully submerged ba ito or partially submerged orifice. Again, recap. Orifice, it is usually a small opening, usually then circular, with a closed perimeter through which the fluid flows. It is used primarily to measure or control flow of fluid. The upstream face of an orifice may be rounded or sharp. An orifice with prolonged sides, such as a piece of pipe having a length of 2 or 3 times its diameter, it is called a short tube. Longer tubes, such as culverts under embankments, are usually treated as orifice, although they also may be treated as short pipes. According to shape, orifice may be circular, square, or rectangular in cross-section. The circular sharp-crested orifice is most widely used because of the simplicity of its design and construction. Okay, next slide. So we have here a general case of fluid flow para sa ating orifice. The figure below shows a general case of fluid flow through an orifice. Let piece of A and piece of B, the air pressure in chamber A and B respectively, and velocity A, B, the velocity of upstream normal to the plane of the orifice, kumbaga yung velocity approach natin, and consider point 1 and 2, such as velocity sub 1 is equals to velocity A, velocity sub 2 is equals to velocity B. And writing the energy equation between these 2 points, neglecting losses, meron tayong, kumbaga, E sub 1 is equals to E sub 2. So ito yung ating total energy head. So summation siya ng lahat ng mga energies, kinetic energy, pressure energy, and elevation energy. So we will be, mas simplify natin siya, and ang ating velocity sa ating chamber B will be square root of 2g, open parenthesis h, plus v sub a over 2g plus yung pressure natin sa A minus pressure sa B over the unit weight. So ito yung ating nagiging formula para sa ating velocity sa ating chamber B. Okay? So sorry, tiko. So next slide. So yung mga summation lang ng ating orifice equation. So we have a theoretical velocity, V sub t is equals to square root of 2gh. Yung h natin is the head upstream minus the head downstream, or is the total head producing flow in meters or feet of the fluid flow. It can be noted as the sum of the flow energy upstream minus dun sa ating flow energy downstream. Or ito ang kanyang formula. H is equals to yung kumbaga, yung sa section 2 ito, elevation section 2, elevation section 1. Okay, so yung actual velocity, V, is equals to coefficient of velocity times a square root of 2gh. For theoretical discharge is equals to acceleration, sorry, area ng ating orifice times dun sa ating theoretical velocity na square root of 2gh. And then para sa ating actual discharge, Q is equals to C times area times square root of 2gh. So here we will discuss the different device coefficient. So para sa ating discharge, yung ating C or C sub D, it is the ratio of actual discharge to a device, through the device to the ideal or theoretical discharge, which could occur without losses. This may be expressed as C or C sub D is equals to actual discharge over the theoretical discharge. The actual discharge may be accomplished by series of observation, usually by measuring the total amount of fluid passing through the device, known as period. The theoretical value can be accomplished using the Bernoulli's theorem, neglecting losses. Next is yung ating coefficient of velocity, represented as C sub V. It is the ratio of the actual mean velocity to the ideal or theoretical velocity, which could occur without losses. This may be expressed as C sub B is equals to actual velocity over the theoretical velocity. And then, yung ating device coefficient para sa contraction or coefficient of contraction. It is the ratio of the actual area of the contracted section of the stream or nung jet to the area of the opening through which the fluid flows. So this may be expressed as C sub C is equals to area of the stream or known jet over the area of the opening. So next here is yung the relationship between these three coefficients. So yung ating coefficient of discharge is equal to the coefficient of contraction times the coefficient of velocity. So yan yung kanilang relationship. So yung actual discharge is Q is equals to C times theoretical discharge. So it's also, yung Q natin is actual area times actual velocity or yung ating A times V. So ipang ano lang natin siya, i-incorporate natin siya here. So meron tayong discharge na C sub C times A times C sub V times VT. But QT or yung ating theoretical discharge is equals to area times theoretical velocity. So masisimplify natin yung ating discharge sa a coefficient of contraction times coefficient of velocity times the theoretical discharge. So we have here. So pwede pa ito mas-simplified again here kasi yung ating coefficient of discharge is C sub C times C sub B. So ito lang siya. So same lang yan sila. Ito silang dalawang ito. Na-expand lang ito siya. So here meron tayong mga coefficient para sa ating orifice. So meron tayong table for this. So, much better na ihatag na lang yung mga table na ito. So, this PowerPoint, nabigay ko naman ata ito sa inyo. So, orifice coefficient, the coefficient of discharge varies with Reynolds number. It is no constant for a given device. Above figure shows the coefficient for vertical, sharp edge orifice. The table below is the discharge coefficient for vertical, sharp edge circular orifice discharging into air at a 15.6 degree Celsius or 60 degree Fahrenheit. Okay, next slide. Meron tayong values or various values of, nakulitin natin, values of age in various conditions. So, ito siya. Ibibigay ko din itong PowerPoint na ito, or I think nabigay ko na din talaga sa inyo. So please, paki-review para ma-internalize ninyo itong mga different values ng age natin. Next, recap tayo dun sa contraction of the jet. So itong phenomenon na ito, let's rediscuss it. So the figure shown represents the cross-section of a fluid through a vertical sharp edge orifice from a reservoir to the atmosphere. The fluid flowing is coming from all directions upstream from the orifice as they leave the orifice. They cannot make an abrupt change in their direction, and they move in a curvilinear path, thus causing the jet to contract for a short distance beyond the orifice. So as you can see dito sa ating figure, yung pinakamaliit na niyang diameter is yung ating vena contracta. The phenomenon is referred to as the contraction of the jet. The section of the jet where the contraction ceases is called the vena contracta, which is approximately located at 1/2 of the orifice diameter from the upstream phase. Okay. Next slide. So we have here orifice under low heads. So when the head of a vertical orifice is small in comparison with the height of the orifice, there is an appreciable difference between the discharges. Consider the rectangular section of length L and height D as shown, with both of the surface of the jet subject to atmospheric pressure. The theoretical discharge through an elementary strip of length L and height DH is, we have the following derivation here. So let's proceed sa kanyang simplified form. So yung discharge natin with the orifice under low heads is equals to 2/3 C, or yung ating coefficient of discharge, times sa ating square root of 2G times L times sa kanyang height sub 2 to the power of 3/2 minus height sub 1 to the power of 3/2. Okay, be familiar sa ating formula na ito. Next, yung head loss. Head loss through venturimeter, orifice, tubes, and nozzles may be expressed as equals to, open parenthesis, 1/CV squared minus 1, close parenthesis, and then open parenthesis, 1 minus area sub 2 over area sub 1 squared times V squared over 2G. Next, if the orifice or nozzle takes off directly from tank where area 1 is very much greater than area 2, then the velocity approach is negligible, and the expression may be reduced to 1/2 1/2 1/CV squared minus 1 times v squared over 2g. Yung v natin is yung actual velocity. Next is yung ating venturimeter. Venturimeter is an instrument in measuring the discharge through pipes. It consists of a converging tube A and B. Converging tube AB. Ito siya, AB. Which is connected to a main pipe at the inlet at A. Kumbaga, ito yung ating main pipe ba? Banda dito. And ending in cylindrical section BC. Okay, inlet natin. Ending dito, BC. Yung throat. And diverging section CD, here, CD, which is connected again to the main pipe or yung ating outlet D. The angle of divergence is kept small to reduce the head loss caused by turbulence as the velocity is reduced. Okay. Next slide. Consider 2 points dun sa system natin, 1 at the base of the inlet and 2 at the throat. And the writing of the equation between these 2 points, neglecting head loss, will be, dito tayo sa kanyang simplified equation. So V sub 2 squared over 2g minus V sub 1 squared over 2g is equals to a pressure sub 1 over unit weight plus yung elevation natin sa section 1 minus pressure sub 2 over unit weight plus dun sa elevation natin dun sa section 2. The left side of the equation is the kinetic energy. Here, kinetic energy natin to. The right side is the potential energy. Ito naman. Neglecting head loss, the increase in kinetic energy is equal to the decrease in potential energy. This statement is known as the Venturi principle. The difference in the pressure between the inlet and the throat is commonly measured by means of differential manometer connecting the inlet and the throat. If the elevation and the difference in pressure between 1 and 2 are known, the actual discharge Q can be solved. So yung ating discharge will be Q equals to C times Q sub T, or yung ating coefficient of discharge times the theoretical discharge. The theoretical discharge can be found once yung ating velocity sub 1 and velocity sub 2 is known. Next, yung ating nozzle. Nozzle is a converging tube installed at the end of the pipe or hose for a purpose of increasing the velocity of the issuing jet. So, example ng nozzle natin is yung ginakabit natin dun sa hose natin para kung magdilig tayo ng halaman. Tapos, gusto natin na abutin yung pinakamalayo, kumbaga, tinatamad ka na natlapitan yung ating halaman. So, gagawin mo niyan, yung nozzle or dun sa tip ng ating hose, di ba parang isi-squeeze mo yan or liliitan mo yung ating opening para mas malayo yung aabutin ng tubig. So, yan yung concept ng ating nozzle. The discharge of a nozzle can be calculated using the equation na Q equals to C times AN or yung ating area at the nozzle tip times square root of 2GH. Yung H natin is the total head at the base of the nozzle. The following table gives the mean values of the coefficient for water discharging through a nozzle, having a base diameter of 40 mm and the coefficient of contraction, which is 1.0. So please, paki-review nitong ating table. So head loss through nozzle, ang kanyang equation is equals to, open parentheses, 1 over CV squared minus 1, close parentheses, and then open parentheses, 1 minus area sub 2 over area sub 1 squared and then v squared over 2g. Next is yung ating where. Where are the overflowing structures which are built across an open channel for a purpose of measuring or controlling the flow of liquids? Wheres have been commonly used to measure the flow of water, but it is now being adopted to measure the flow of other liquids. The formula and principles that will be discussed are in general, example, applicable to any type of liquid. So meron tayong classification of wares. It is according to its shape. The ware may be rectangular, triangular, and trapezoidal, or circular, parabolic, or any other regular form. But the most commonly used shape are rectangular, triangular, and trapezoidal shapes. And according to the form of the crest, wares may be sharp-crested or broad-crested. The flow over a ware may either be free or submerged. If the water downstream from the ware is lower than the crest, the flow is free. But if the downstream surface is higher than the crest, then the flow is submerged. So meron tayo dito definition ng ating ware. So kumbaga meron tayong typical cross-section ng ating ware. So here meron tayong kanyang. So we have here the nap, the crest, the weir plate, and channel bed, yung drawdown. So let's discuss or yung kanyang mga description nitong mga parts na ito. Nap is the overflowing stream in a weir. Crest of weir, kumbaga the edge or the top surface of the weir, with which the flowing liquid comes in contact. Contracted weir, which is the weirs having sides sharp edge, so that the nap is contracted in width or having end contractions, either one end or two ends. Meron tayong suppressed weir or full width weir. Weirs having its length L being equal to the width of the channel, so that the nap suffers no end contractions. And then meron tayong drop-down curve, the downward curvature of the liquid surface before the weir. And then last, yung ating head, H, the distance between the liquid surface and the crest of the weir measured before the drop-down curve. Okay. So yung standard weir factor, kumbaga yung ating C sub W formulas, numerous equation have been developed for finding the discharge coefficient, yung ating CW, to be used. Meron tayo ditong Francis formula, Rebock and Chow formula, and Bazin formula. For Francis formula, we have the weir factor na 1.84, open parentheses, 1 plus 0.26 times H over D, and then to the power of squared. And then sa Rebock and Chow formula, we have in SI unit, CW is equals to 1.8 plus 0.22 H over P. H over P is yung ating i-discuss later. Okay? So, para sa English unit, yung ating weir factor is 3.27 plus 0.40 H over P. For the Bazin formula, yung ating weir factor is equals to 0.5518, open parenthesis, 3.248 plus 0.02161 over h, close parenthesis, and then open parenthesis, 1 plus 0.5 h over d squared. So for the last PowerPoint for this video, we have the standard weir. The following standard specification must be applied to a standard rectangular weirs without end contractions. So first, the upstream face of the weir plate should be vertical and smooth. The crest edge shall be level, shall have a square upstream corner, and shall be narrow, that the water will not touch it again after passing the upstream corner. And then the side of the flume shall be vertical and smooth, and shall be extend a short distance downstream past the weir crest. The pressure under the nap shall be atmospheric. And then last, the approach channel shall be of uniform cross-section for a sufficient distance above the weir, or shall be provided with baffles that a normal distribution of velocities exists in the flow approaching the weir, and the water surface is free of waves or surges. So again, this is our last PowerPoint for this video presentation. Next video presentation is the following problem solving with regards sa ating na topic sa video ito. So thank you, and see you next video. See you sa next video.